Okay, so in this second video, I'm going to talk about how electromagnetic waves propagate through space and how to calculate the energy that is transported by them. Okay, so this gives you, I think, a really clear picture of what an electromagnetic wave looks like. Like some things to point out. So this is like an electromagnetic wave propagating through space. You can see that the electric field is in one plane. The magnetic field is orthogonal, so 90 degrees to that plane. And then the propagation direction is 90 degrees from both of those. So like you can actually use your right hand to figure out like the direction of propagation, and I'll like write this out mathematically in a second. But if you point your fingers in the direction of the E field and then you curl them in the direction of the B field, your thumb shows the direction of the propagation. So like the video is difficult because it's going to be reversed, but like put your right hand, like point up, like point your fingers up in the direction of the E field, right? Like the E field is pointing up. So point your fingers up, curl them out like of the page in the direction of the magnetic field. Okay. And then your thumb is pointing to the right. So like in the positive X direction, right? If this is like, so if the E field is pointing in the positive Y direction and the B field is pointing in the positive Z direction, then the direction of propagation would be positive X. Okay. So that's another like way you can use the right hand rule to like figure out wave propagation direction. Some other like things to note are that the peaks and the troughs of these waves. So like here's a peak, here's a trough. The peaks and the troughs of electric waves or electric field, the electric field, so the E field, um, coincide, like they overlap. So they coincide with the B field. So like the peaks, like when there's a peak for an E field, like here, there's also a peak for B field. Okay, and same thing with the troughs. Okay. Um, this leads to another observation, which is that the electric and magnetic fields are the same ratio at every point along the wave. Okay, so let me write that. Like the E and B fields are the same ratio. Like they're changing as at the same function at every point along the wave. Okay. And the ratio is the speed of light. Okay. So like if you take the electric field at any point and you divide it by the magnetic field at that same point, right? Like if I take this point and I divide these two numbers here, then I get the speed of light. If I divide these two numbers, like the peaks, I get the speed of light. Okay. So C equals the speed of light. And the speed of light is, remember, is 3 times 10 to the power of 8 meters per second. Okay, which means that all E and M waves propagate at the speed of light, which is like a fundamental sort of like truth. And again, it governs like so much of the world around us, you know, like so EM waves propagate at the speed of light. Okay, so it doesn't matter whether you're talking about a microwave or an X-ray or visible light or a radio wave. All of those different examples of E&M waves propagate at the speed of light. Okay, and I posted a video on Collage that gives you like an overview of like something called the electromagnetic spectrum, which just basically talks about like all of the different types of E&M waves, right? From like microwaves to X-rays. The visible light spectrum is in the middle there, and like talks about how, you know, the wavelength and the frequency of those different types of radiation change. Okay, and I mean it's like a pretty basic video, but I think it's a good overview of like connecting like this idea of how E&M waves propagate through space to like what is an E&M wave, and like, you know, different E&M waves are like important to our everyday lives. Okay. Um, so yeah, and then like another kind of obvious point from the diagram is that the E field is perpendicular to the B field. Okay, and that both fields are perpendicular to the direction of propagation. So again, you can use your right hand to figure out the relationship between those three things. Like, so direction of propagation, like the V, right? So like this wave is propagating in this direction. Okay, it's a transverse wave that's moving through space in that direction. Okay. So again, in Collage, I added a section on like what this means in terms of like telecommunication, like if you have a transmitting antenna and a receiving antenna, like how that wave like propagates through space, like such that the receiving antenna can pick up the signal. One of the things that we're going to do next week is like a very brief tutorial on that, like how, you know, waves are transmitted through space through antennas. And I also posted a video of like an interesting demonstration that was done by the Harvard lecture demonstration team. And so you can watch that on Collage if you're interested. Um, okay. So, oh yeah, so I wanted to do an example problem. Okay, so let's say that you've got an E&M wave that has a maximum E field of 600 volts per meter, and I want to know what the maximum B field is. Okay, so this is this is pretty straightforward because I know that at any point along the wave, so if we're talking about the max, so EO is usually like the symbol that we use for max, like E field, and like B, like BO is a max B field. Okay, and remember those two things are going to line up, right? Like from this picture, like the peak of the E field lines up with the peak of the B field. Okay, and the ratio of the two fields at any point along its propagated wave is just E over B equals C. So therefore B naught is going to equal E naught divided by C. So if I know that the E field at its maximum value is 600 volts per meter, and I divide that by the speed of light, I just get 2 times 10 to the negative 6 Teslas, which is going to be the maximum value for the B field. And I mean, something to notice here, which I think is interesting, is that you know, the V field is much smaller in magnitude than the E field, and that's, I mean, that's typical. Okay. Now let's talk about energy. So electromagnetic waves carry energy through space via these oscillating electric fields and magnetic fields. And that energy can be quantified in 3 different ways, 3 kind of like quantities that all have to do with energy, but they mean different things. So the first is energy density. the second is something called the Poynting vector, and the third is something called intensity. And these all, again, they're all connected to energy, but they all have like slightly different physical meanings. So let's talk about density first. So density, which is just like the symbol for which is just again mu, is just the amount of energy stored per unit volume in an E&M wave. Okay. The formula for it is just 1/2 E naught. So this is the electric permittivity of free space, which is just a constant, times the electric field squared plus 1/2 B squared, the magnetic field squared, divided by the magnetic permeability of free space. Okay, which again is just a constant. Okay, so that's how you calculate the energy density. And it's pretty straightforward. It's just a matter of like, if you know the E field and you know the B field, you plug those numbers in, you put the constants in, and then you've got it. Okay, one thing that I will note is that it's like the energy is shared equally between both fields, between the B and the E fields, okay, which is kind of interesting. Okay, now let's talk about the Poynting vector. So the Poynting vector is a rate of energy flow through a unit area. It's like, it's analogous to flux from an energy perspective. Okay, it always points in the direction of wave propagation. Okay, so remember, like, so in terms of its direction, let's say you have an E field that is pointing in the positive Y. You have a B field that is pointing in the positive Z. And you want to know, like, what's the direction? Oh, and the Poynting vector, the symbol for it is capital S. So what is the direction of the Poynting vector? Well, again, you can use your right hand. Point your fingers in that. Well, let me show you first the formula for it. So the Poynting vector is 1/mu naught times the E field crossed with the B field. Okay, so this is the cross product. Okay, so remember the cross product. I use my right hand to figure out the cross product. I point my fingers up in the direction of the E field. I cross them with the direction of the B field. So I curl them out because the B field is pointing towards me. My thumb points to the right, so that's going to be positive x. So the Poynting vector would point to the right, which would be the direction of the overall propagation of the wave. Okay, so that's pretty much all there is to the. I mean, these things are kind of basic definitions, so they're not that profound. The intensity is just another way of like expressing energy, and it's basically the average power transmitted per unit area of the wave. Remember what power is from mechanics. Power is energy divided by time. Okay, and you can sort of think of intensity as the time average of the Poynting vector, of like the absolute value of the Poynting vector. Okay, which would be written like this. So absolute value of the Poynting vector, and then these little pointy brackets mean time average. So intensity can be thought of as the time average of the magnitude, which is where the absolute values lines come in, of the Poynting vector. Okay, and like just to summarize, I'll show you, there's actually three different ways of writing intensity. There's three different expressions for it that are all kind of like I derived like how you go from one to the other on collage. But just to summarize like the three things, electromagnetic waves carry energy, and you can think of that energy as like the amount of energy is expressed by the energy density. Okay, so that's like mu. Okay, so electromagnetic waves carry energy, like how much, then you calculate the energy density. They move that energy through space, and like that is expressed by the Poynting vector. So the Poynting vector is kind of like a flow, and they deliver it to surfaces, and that's like how I think of like intensity is like the amount of energy that is like delivered. So this little sentence that I wrote out for you here is just like how I organize this information in my head. Like E&M waves, they carry energy. The amount of that energy is defined by the energy density. They move that energy through space, and I can calculate the flow of that energy with the Poynting vector. And they deliver that energy to a surface, and that's where the energy intensity comes in. Okay, so let's talk about the three different ways of calculating energy intensity. So you can just multiply C times E naught times the electric field squared. That's one way. Another way, and again, you can like derive these. I did it for you on collage just so you can see like how you go from one to the other. Is just C times the maximum magnetic field squared divided by 2 times mu naught. And then the third way is the maximum electric field times the maximum magnetic field divided by 2 times mu naught. So any like these are three equivalent. I show in collage how these three are equivalent. And I mean, I don't know, like you don't really need to know like how to derive them. And they're different, like different forms of them are useful in different, like depending on what you have and what you're looking for. Okay. I think I wanted to end this with an example problem. Again, I think one that will help you with the challenge, at least one, possibly two of the challenge problems. Okay. So let's say you've got two electromagnetic waves and they're traveling through empty space. One of them has an amplitude of 300 volts per meter. The electric field amplitude is 300 volts per meter, and the other is double that, 600 volts per meter. A student claims that wave 2 carries twice as much energy because its electric field is twice as large. And we want to like calculate a bunch of things, but we also want to know like, is that student's claim correct? Okay. So the first thing we want to do is for each wave, calculate the magnitude of the Poynting vector. Okay, so the Poynting vector, remember, can be calculated just by, okay, so so A. So the Poynting vector is just 1 over U naught times E times B, right? Okay, so for S1, okay, so I'm given the electric field is in both cases for both waves, but I need the magnetic field. So I need the magnetic field for both waves. Okay, so I can just use the technique that I just showed you in the previous example problem to calculate that. I'm not going to make it into a vector because I'm just going to calculate the magnitude. So the first magnetic field, remember, I can just take the electric field and divide it by the speed of light. So the first electric field is 300 volt per meter. I divide that by 3 times 10 to the power of 8 meters per second, and I'm going to get 1 times 10, 10 to the power of 6. Oh, of -6, sorry, Tesla. Okay. And then B2 is just going to be E2 divided by C. So same technique, 600 volts per meters divided by 3 times 10 to the 8 meters per second. So that's going to give me 2 times 10 to the power of -6 Tesla. Okay, so now I'm going to use those values to calculate the Poynting vectors for both waves. So S1 is going to be basically like electric field times magnetic field divided by mu naught. So mu naught is the magnetic permittivity. It's basically like how responsive a material is to a magnetic field. It's a constant. This wave is traveling through air, so we use like the magnetic permittivity. This is the magnetic permittivity of like free space, like just a vacuum, since that's what the wave is traveling through. And it's again, it's a constant for like different materials. Like, you can look up the magnetic permittivity of like different materials, but we're mostly talking about waves propagating through air or a vacuum. Okay, and so the value for that is what is it? It's 1.26 times 10 to the -6 Tesla meters over amps. It's a weird unit. But like what it is, it's basically like how responsive a material is to a magnetic field, like how much it responds when it's exposed to a magnetic field. Okay, it's not something you really need to worry about. It's just a constant. So okay, so we're going to calculate the Poynting vector of wave 1. So that's just going to be 300 volt meters, which is the electric field times 1 times 10 to the power of -6 Tesla, which is the magnetic field, divided by that constant, right? 1.26 times 10 to the -6 Tesla meters over amps. Okay, so that's going to give me 238 watts per meter squared. Okay, which if we look at what the definition of a Poynting vector is, should make sense to you, right? The Poynting vector is the rate of energy flow. So through a unit area. Okay, so the unit area is the meter squared. That's the unit on the bottom. And the energy flow, the rate of energy, which is just energy per time, is power. And that's measured by a watt. Okay, so the W is the watt. And that's a unit of power. I don't know if you remember that from mechanics. Okay, and that's energy per time. Okay, and the meter squared is just an area. So this makes sense given what a Poynting vector is, right? A Poynting vector is the energy per time per area. Okay. And I mean, if you're curious about how the units break down, I mean, in terms of like, okay, so like from here, like to doing a dimensional analysis, we've got like this area, or sorry, that's not area, that's amps. A here in this unit here is Tesla meter over amp. Okay. So from a dimensional analysis here, this unit, if we just look at units, is just amp times volt times Tesla. And then on the bottom, we've got Tesla and we've got meter squared. So the Tesla cancel with the Tesla. And so we're left with amps times volts over meters squared. Okay. An amp, what's an amp? An amp is a coulomb per second. Remember from current, okay? And a volt is a joule per coulomb. Okay, remember the definition of a volt. Okay, so A times V is a joule, like the coulombs. So A times V, the coulombs cancel, is a joule per second. And a joule is a Newton meter. So that's a Newton meter per second. And that's the same as a watt. Okay, so that does actually check out. Okay, I hope you guys followed that. So A times V is just the top part of this here. Okay. An amp is a coulomb per second. A volt is a joule per coulomb. I multiply those two things together, I get a joule per second. A joule is a Newton meter. A Newton meter divided by a second is a watt. So the unit does actually cancel, or sorry, like it does check out, which is like reassuring in terms of like what a Poynting vector is. So S1 is 238 watts per meter squared. And did I do the calculation? Yes, I did. Okay, so S2, I just exact same procedure. You can do that on your own. It's 952 watts per meter squared. Okay, so now I've completed part A. Part B asks me to compare the energy flow of the two things. So I'm going to divide S2 by S1. So that's 952 watts per meter squared divided by 238 watts per meter squared. And that gives me about 4, right? Like if you divide those two numbers out. So the claim that the energy doubles is not correct. So therefore, okay, let me just insert a page. So therefore, the claim that the energy doubles is incorrect. Okay. The energy actually quadruples. Okay. And this is an important kind of realization, because energy flow defined by the Poynting vector S, energy flow scales, it's proportional to the electric field times the magnetic field. Okay. It's also proportional to the electric field squared. Okay. So if you double, therefore, if you double the E field, you in turn double the B field, and therefore the energy quadruples. And this is an important, I mean, this like if you go on in physics, this is it's a fundamental like truth that is important in many fields. Anything basically that has anything to do with electricity and magnetism is sort of like built on this premise of like the relationship between the E field and the energy. Okay, that's pretty much it. I think like just with those two example problems that I've gone over in each of the two videos, it should set you up very nicely for the challenge. And like I said, the topics this week are like relatively light compared to other weeks. And so I think I've hit all the important things in between the two videos, but please do take a look. I put a lot of time into putting the collage together in terms of like the other like demo videos and the content in the little blocks. So like take a look at those, and yeah, I'll see you next week.